Okay. Okay, so I had question 1, and the ball is moving radially outward, so this way, with the velocity of 4.3 inches per second, and has a radial acceleration of 4.6 inches per second squared. And it is located 2.3 inches from the center of the disc. So it's a ball bearing, and this disc is being rotated, and this ball is moving. Okay. So I was tasked with finding the magnitude of like the radial velocity in order to make the total acceleration of this disk 0. So I had to use this equation So this is the radial acceleration which is like theta dot dot, and then the tangential acceleration would be like the acceleration from like here. Yeah. Okay. So the equation give me 2 seconds. So the tangential acceleration wait, is this part A or part 1? Okay, my bad. Wrong number one. That's why I was lost. Okay. Okay, let me correct myself. The total acceleration is equal to I wrote this backwards, but the tangential acceleration minus the radial acceleration. So this equation would be so this is the angular velocity squared, and this is the angular acceleration. And the R stands for the radius, or like the distance the ball bearing is from the center of the circle.
Actually, what we have written in the second line is actually a radial acceleration. That's not the tangential acceleration included. Tangential acceleration is not included in it. So that's right. That's all that you need right now. So you can call that a radial.
Oh, okay.
So you can't just add AD and AR. They're in different directions, right? So these are vector equations. So you have to add it appropriately. So anyway, you don't need the first equation as of now. You can change the subscript in the second equation to radial.
Okay.
You can erase the first line. You can erase the first line. You don't need to.
Okay. And we want this to be 0. So 0 is equal to negative r theta dot squared plus r theta dot dot. So you add this to this side. Because we already know the value of this, which is 4.6 seconds. These two are equal to each other, so we can make this equal to 4.6. And then we know R, which is 2.3. So you divide both of them by 2.3. This will give you 2. And then you take the square root. And this is equal to 1.41.
Angular velocity, theta dot, so it's not inches per second. What is it?
What'd you say?
Theta dot is an angular acceleration, angular velocity.
Yes.
So the unit is not right.
Huh? Yeah. Oh, good. Sid, did you want me to erase this?
You can erase that.
Okay.
Yeah, you can erase the one. Just leave the diagram. This question is similar, and it asks for the angular acceleration rather than the velocity, and just the numbers are a little different too. So it's 2.4 here inches, 3.3 inches per second, and then 4.3 here. And so I'm tasked to find theta dot dot. So we know that A equals this is like the radial component and the angular component, and so we want A equal to 0. So we want both of these to equal 0. So So this can just be rewritten as that. And then we want these to equal 0. So let's start here. R data squared equals 0. So we actually know some of these values. So R is 2.4 inches. Then R dot velocity is 3.3 inches per second. And then R double prime is 4.3 inches per second. And then theta, see here. Yeah, so we actually don't know theta naught, but that's theta naught, but we're solving for that and then using that theta dot here to find theta double dot. So we have 4.3 minus 2.4 theta dot squared equals 0. And then solving for theta dot, you have the angular velocity being 1.34 radians per second. And then we want this component to equal 0 as well, so I'll write that here. R plus 2, 0. And then we have 2.4 theta plus 2. And then we just solve for the angular acceleration to be negative 3.68 radians per second squared. But they asked for magnitude, so you just take the absolute value and you get 3.68 radians per second squared. Okay. My problem was relatively simple. What it was is that this plane, excuse the drawing, is going at 467 knots. And let's call this point A. It turns upwards. It does an upward pitch with a turn radius. Let's call this R is equal to 1.8 kilometers. And what it wants is what are the g-forces that this pilot experiences. So the g-forces is basically going to be highest when he does this maneuver. Like at point A, it's going to be highest because we have a centripetal force and a gravitational force that are at their max. And then the g-forces that you feel is, so let's call this gf is equal to fc plus fg. So that's what he feels. So let's first convert the units. To one standard system. So 467 knots is equal to 240.25 meters per second. And then obviously 1.8 kilometers is equal to 1,800 meters. So we have
to calculate the force. So the total force, we're only going to consider the centripetal force right now because we already know the gravitational force. So the total force from the centripetal, so Fc, is equal to dp dt parallel plus dp dt perpendicular. This is with respect to point A, so I'm going to put point A right here. Since he's turning in a perfect uniform circle, we're going to cancel this out, and we're only going to look at with respect to A, dp dt perpendicular. Now from physics 1, we know that this formula is equal to mv squared over r. And what we can do is plug in v as 240.25, r is 1,800, and then the mass we don't know, but we really don't need. So what we get is this one. Plugging in the numbers, we get centripetal force is equal to 32.07 times m newtons. So if we say, we know that force is equal to ma, so we say force C is equal to ma, and we say 32.07 m is equal to ma. We know that a, let me put the vectors, we know that a is equal to 32.07 meters per second squared, which if you put this into g-forces, which is dividing by 9.81, so divide by 9.81 meters per second squared is equal to 3.27 Gs. So the pilot feels 3.27 Gs from the centripetal force, but we also have the gravitational force that he's in, so we just add 1 G because G force is equal to centripetal plus gravitational. So we say GF is equal to 3.27 plus 1, which is 4.27 Gs. That is the answer. Yeah.
Thank you. All right, this is an interesting problem. So you have, let's call this Earth, and we're going to call this the ISS. Information you're given, radius of the Earth. Actually, we don't need that. This is going to be R. This distance here, I'm going to call D. The ISS is moving at some linear velocity. I'm going to call VI for ISS. And a hammer is thrown from the ISS in this direction. I'm going to call this VT for V thrown. And all of these have values, so I'm just going to write them down really quick. And also, my coordinate system is going to be X, Y. I had J hat. So this is the 7.66 kilometers per second in the I hat. And the hammer is thrown at 11 meters per second in the J hat. So the very first thing to do is to see how the system is moving before the hammer is thrown. And that's really easy to do because we can just find the angular velocity because we have all the information. We have the radius and we have the velocity. So first, the angular velocity is v over r, but in this case, r is actually r plus d. So, and you only care about the magnitude of the velocity, so it's v over r plus d, and I'm not going to show the calculations for redundancy. That comes out to 1.127 times 10 to the negative third, and the units for this are radians per second. Okay, so now it gets interesting because we want to find the goal of this whole problem is to find the angular acceleration of the hammer with respect to the ISS as it's rotating around. So if you imagine, if I'm just looking at the Earth straight on and the ISS is moving and they throw a hammer, it'll move linearly. But if I'm looking at with respect to the ISS and I throw the hammer, it moves in a curved direction. So you have to account for that curve because this is with respect to the ISS. So the way that you do that is you find the tangential acceleration with respect to the ISS, and then you can find the angular acceleration from that. So the tangential acceleration by the Coriolis effect, I'm just going to call it t, is equal to 2 times your angular velocity in the k-hat direction crossed with the velocity at which an object is thrown. And so in this case, that velocity is v of t. And we only need the magnitude, so I'm going to be taking the magnitude of this. So this equals the magnitude of the determinant of I, j, k. And so the angular velocity we just calculated here, so it's in the k-hat direction, so 0, 0, and then 2 times 1.127 times 10 to the negative third. And then the velocity at which it's thrown at is 11 meters per second in the j-hat, so it's 0, 11, 0. And then we want the magnitude of this whole thing. And so whenever you actually calculate out the cross product, you get about, you get a negative 11 times 2 times 1.127 times 10 to the negative third. And then we want the magnitude of all of this. The negative goes away, and that comes out to 0.0248 meters per second squared. So this is the tangential acceleration of the hammer after it's thrown. And we want the angular acceleration. So similarly, how we found angular velocity from tangential velocity, we can just say that the angular acceleration equals the tangential acceleration, magnitude of tangential acceleration, over the radius again, which is 0.0248 over r plus d. And that comes out to 3.649 times 10 to the negative 9 radians per second squared. The question asked for microradians per second squared, so that's 0.003649 microradians per second squared. Thanks. Yeah. Yeah, because when you want the angular velocity, you need this whole thing. So, yeah, it's just r plus t.
Circular motion, so you're looking at the radius of that circle.
Are we going to go over this in the slides?
Yes.
Okay, so we have a point P. It moves along this path with, and this is the equation. So this is S is equal to C times T to the third power, where C is equal to 0.7 feet per second cubed. And at t equals 2.3 seconds, the acceleration is equal to 18 feet per second squared. Okay, I can put the phone down. So the magnitude of the acceleration squared is equal to the radial acceleration plus the tangential acceleration squared, which is equal to v squared over r squared. So this is just the second derivative of the initial equation. And this is the velocity. Yeah, the velocity divided by the radius of curvature. So this is what we're trying to find. So by the way, I did this like 2 a.m., so I'm trying to remember what exactly I did. I'll just start with this. So this equation is 0.7 t to the third, substitute in c. So the first derivative would be 3 times 0.7 t squared, which is our velocity. And then the second derivative is 6.07 t. And I did not write down those numbers. Times 2.3 squared. At t is equal to 2.3, this is 11.109, and then this is equal to 9.66. But let me just double check real quick. Yeah, it's 9.66. Okay, so now that we have those,
When you get 3.07?
3 times. Sorry.
Oh.
Yeah. Okay. And this is okay. So now that we have that, this is 18 squared is equal to 11.109 squared divided by r squared plus 9.66 squared. So once you square this, and take it from this, you'll get okay, actually, then solve that part out. I just simplified it actually. So what I did was I expanded this. So I turned this to this. So I just like added in the exponent. So this became 15 to 30 over r squared plus 9.66 squared equal to 18 squared. And I solved for r, which is r squared is equal to 15 squared. So this is the 18 squared and this is the 9.66 squared. And then taking the square root of that, r is equal to square root of 66.02, which is equal to 8.125, 8.13 feet.
Thank you. So we have a movement along the curve. Velocity, tangential velocity here is v, meters per second. And then we have an acceleration this way. And this is the acceleration has the tangential component and the perpendicular component. So we have this. This is the theta between the tangential component. And we're given that v equals 2.1 meters per second. A is 38.6 meters per second squared. And theta is 23.9 degrees. And they're asking for dv dt, which they said is just the second derivative of the position. So that's since the velocity is moving here, it's essentially the tangential component of the acceleration. So we can say this is a tangential, which is just in this diagram. We can see that if I denote this side as positive and this side as negative, then it's negative a cosine theta, because this is adjacent and this is the hypotenuse of the triangle. And we can plug in negative 38.6 meters per second squared, and then cosine of 23.9 degrees, and we get that dv dt equals negative 35.29 meters per second squared. Yep.
Yeah.
My question was kind of similar. I'm just gonna like clarify, like this is the positive x, this is the positive y. For me, I had different values for the motion. So the velocity was 9.5 meters per second. Acceleration was 34.4 meters per second squared. And theta was 20.4. And I was tasked with finding the radius of curvature that this motion is going along. And so the relationship between acceleration, velocity, and curvature, or not curvature, radius of curvature is that the normal component of acceleration equals the magnitude of velocity squared over radius. And so just solving for radius, you get magnitude of velocity squared over acceleration. That's normal to motion. So just setting up acceleration as a vector, so we can find the normal component, you get A equals the magnitude of A, which is 34.4, times its unit vector, which is negative cosine of theta, because this is in the negative x direction, and then positive sine of theta, because this is in the positive y direction. And so this sine of theta is what actually gives us this normal component of acceleration. So r ends up equaling, velocity is 9.5, so 9.5 squared over the normal component is 34.4 sine of 20.4, and that comes out to 7.527 meters.
Okay, so once again, I got stuck with the simple problems. We had for particle P, the r vector, OP. I'm assuming O is the origin, is equal to AT squared plus B, AT squared in the I hat direction plus BT cubed in the J hat direction plus CT to the 6 in the K hat direction. And we are given A is equal to B, 1.1 meters per second squared. B is equal to be 1.7, I believe. Yeah, meters per second cubed. And then C is equal to 1.9 meters per second to the 6th, whatever that means. So we need to find the V of P dt. So what I figured out what to do. So first we take, with respect to O, dr of P dt, which comes out to be 2AT in the I hat direction plus 3BT squared in the J hat direction plus 6CT fifth in the K hat direction. So next what I did was compute the magnitude of that. This is basically equal to, so drp dt with respect to O is equal to V vector of P. So what I did was compute the magnitude of VP, which turned out to be this monstrosity, 36c squared t8 plus 9b squared t squared plus 4a squared. And then after that, I took dvp dt, which is equal to magnitude of acceleration of p, which is, again, another monstrosity, t 180c squared t8 plus 18b squared t squared plus 4a squared over So I did kind of forget units. This is in meters per second. This is in meters per second because it's just magnitude of velocity. And now this is in meters per second squared. So now if you plug in A, B, C, and then we said t is equal to 0.5 seconds, you get dvp dt is equal to 5.92 meters per second squared, and that is the answer. And the only way I was able to do these derivatives is with the help of a calculator.
Is there a loop? Explain like the second line.
This?
Yeah.
It's just the magnitude of this, so it's just these terms squared over the square root.
I think we took a t factor common out, which
Yes, because this, wait, did I?
There would be a 2 with the 10 would be the
Oh.
second.
Wait, yeah. That's why.
Did I miss like a t
You
here?
squared it and then you just put the t out. Because you squared it, you factored out the t squared, then you squared that to its t.
Okay, yeah, I probably just missed that t. And huh? Yeah. Yeah, because A is acceleration and then this is. Oh, that's true. That is true. I don't know if this is acceleration because the first time I actually did it, I thought this was to be true and it yielded different answers. So I'll just leave it at that actually. Yeah. Because you take.
The derivative of a magnitude is different than the magnitude of a.
Oh, right.
So that's the derivative of magnitude, but the magnitude of A is the magnitude of B.
Yeah.
excellent job, guys. That's the remote. Is it powered on? Maybe that switch there. Yeah. One of you said you wanted to go through the problems again on the slides.
You said something like, are we going to go over? Yeah, no, I was just saying like the topics. Like,
Oh yeah, sure. Yeah. Okay, yeah, sure. Just close this. So we can revisit some of the problems in case you need to, but I think you guys did an excellent job in terms of solving it. There's no unique way of solving these problems because there are multiple routes to doing that. From whatever we have learned in this course, as well as I think some of you refer to previous courses like physics, etc. So I think you've brought it out quite clearly. So some of the things that we will be going through will probably make you take a relook at some of the problems you solved, and probably there are more efficient ways of doing it as well. Okay, so let's continue with where we left off in the previous class. We're looking at differential equations because all your equations of motion eventually are going to become differential equations. But even before we get to that, in kinematics itself, we've defined velocity and acceleration as derivatives of the position vector and the velocity. So that leads to differential equations when you know certain quantities and you want to solve for certain other quantities, right? And we looked at the very simple case at the end of last class, where we looked at acceleration just being a function of time. Then all that you needed to do is to go ahead and integrate it once to get the velocity, integrate it twice to get the position vector, and at each stage, of course, you have to apply the initial conditions in terms of the initial velocity and the initial position, so that you can go ahead and do that. But now we are looking at a little more complex situation where your acceleration is not a function of time alone, but it's a function, could be a function of the position and or the velocity as well, apart from being an explicit function of time. So it's in such a case that the straightforward integrations that we were doing becomes a little more difficult. These are more complex governing differential equations, and along with the boundary conditions, it forms a boundary value problem, or an initial value problem rather, because it's in time. And it can't be solved, as I said, through simple integrations, because you don't know R and V, which are also unknowns as much as A, and they are in turn functions of T that are to be determined. Maybe some parts of it might be known, but some parts will be unknown, and therefore it becomes more complex. And essentially you have second order differential equation in R, the position vector, the second order derivative with respect to time in a particular reference frame, let's say the inertial reference frame, is equal to that particular acceleration, which in turn is a function of these two quantities, the position and the position time derivative, both of which are functions of time. And once again, as far as the initial conditions are concerned, it's very similar. You get the initial position and the initial speed, and based on that R naught and V naught, you're supposed to solve for the constants that you get of integration when you're able to integrate that. But as I said, the equations get fairly complicated, and therefore you can't get analytical solutions like what we used to get for for some of the example problems and some problems which you had in this homework as well. And therefore, in general, you will have these kinds of situations, and many a times you might have to go for nonlinear equations to be solved by numerical solvers, and that might become the only option because you don't have an analytical solution. And in fact, that's what almost all of the computational power goes into the solving of the differential equations, especially nonlinear coupled systems of differential equations. There's data saying that more than 50% of the world's supercomputer power is used in solving differential equations. You can see the number of real problems that are governed by such boundary value problems and initial value problems in a mathematical model. And there are some very simple ways of doing it. For example, MATLAB has this function ODE45, and similarly Mathematica has an ND-solve where N stands for numerical. There's also a D-solve, which is a differential solver to get your analytical solutions. So that works only for simpler differential equations relatively, but ND-solve is much more robust in the sense that it can deal with more complex problems. But of course, you wouldn't get analytical solutions, you'll just be numerical solutions. You can always do a parametric study, but nothing like having an analytical solution where feasible, because that gives you a lot more insight into the problem, and which is what we try to extend the limits in terms of trying to solve analytically. If and only if it's not feasible analytically, we go for such numerical solutions. So it's very similar to the example problem that we had looked at earlier, if you remember. In one of your, I think the previous assignment, you had something related to Falcon 9, where we talked about the thrust and the acceleration, the correlation between that. And we said that there are lots of assumptions that were made in that particular thing. In reality, obviously, a solution like that will be kind of crude. It can probably give you certain trends, but it will not give you values that are of significance, which means that an example like that will have to be worked out eventually using numerical solutions, taking into account all of those complexities without making some of those assumptions. So, or you try to make them less stringent. So that's, which is what you would do. So typically you will have the mass distribution. That mass distribution will change as the rocket flies and the propellant is burnt. The propellant configurations comes into picture in terms of, for example, a star configuration or whatever. So the burn rates are going to be dependent on that. You might have, instead of a solid propellant, you could have a liquid propellant. Then the rates at which you're burning the fuel and the oxygen and how you're releasing it, all of those things come into picture. The payload, there might be certain satellites which might be released. If you're looking at multiple satellites being carried by this vehicle, then you might release some of them in different orbits, and then the change in payload will have to be taken into account. Typically, it's a multi-stage rocket in which I think this is 2-stage, if I remember right. So you would drop off one stage to reduce the overall weight, and therefore you'll have to take into account that as well. So there will be certain mass distributions which will be continuous functions, and there will be certain which will be discrete in time. So as you go, it will change abruptly, and you'll have to typically make these as just like the rocket itself is multi-stage, your calculations also will be multi-stage, in the sense that you will divide the overall time domain into parts, and each part will have the final time will become the initial time for the next stage, and then you will try to do that. So I think you got a taste of that in the second problem involving Falcon 9, where it was going vertically first and then took a 45-degree turn, and then it started going that way. So then you had a little more complex situation to deal with. So similarly, as far as from the propulsion, we get data related to the maximum thrust, how the thrust itself changes with time, etc. based on the specific impulse of the propellants involved and burn time, etc., which we already discussed. So all of that has to be incorporated into your mathematical model. It's not that it's what they call rocket science really, but it really is that it's more complex than what we dealt with, and therefore there is a possibility that you may not have analytical solutions, so you might have to go for computer-based simulation, and these will include, of course, apart from the propulsion data, certain data related to the aerodynamics as well, because part of the flight is in the atmosphere and then it goes into space where fairly rarefied atmosphere, and therefore drag might not be a consideration over there. But then initially it will be under the effect of gravity of the planet or whichever entity it is taking. But as it goes, it could be relatively close by to other masses as well, like for example it could be closer to the moon, so the effect of the gravity of both the moon and the earth might have to be taken into account, etc., because it's a fairly large distance that it is flying and the gravitational field changes, and usually what we take as 9.81 is on the surface of the earth, so you'll have to account for your universal gravitational constant times the mass of the entities which are attracting it divided by the distance from the center, which is also one of the points that was brought out in one of the homeworks you had today, because for the International Space Station that you worked out, you were adding the altitude to the radius, so because you want the distance between the two centers of mass of the bodies which are applying gravitational force on each other, right? So now we are going to kind of generalize what we did for 2D to 3D. So this is the 3D particle motion. We will start off once again with the simplest kind of frame of reference, which is the inertial frame of reference. When we don't have an inertial frame of reference, you will have to have multiple frames of reference. You will have certain frames which will be accelerating or rotating, which are not inertial, but might be more conducive to describing the motion. But then eventually you will go on to an inertial or nearly inertial frame of reference, so that then you have to know how to convert from one frame of reference to another frame. And for most parts, when dealing with frames of reference, we might be interchangeably dealing with rigid bodies, because we'll be fixing the frames of reference to rigid bodies like the Earth, etc., and therefore we might use these names kind of interchangeably. As I said, every problem hereafter, even when you're working your assignments, it was okay, you're getting to the solution, but I want you to be a little more accurate in terms of how you go about a dynamics problem, because for these simple problems it might look like it's kind of trivial, but always start with a frame of reference, introduce a coordinate system, and then of course you are all very clear about going with the units and the consistency that you're already doing. But introducing these two is important. I saw in one of the solutions you are looking at dV by dt of a point P with respect to O. So that is not the way typically it's supposed to be written. I think one of you were looking at writing this with respect to O. I don't remember if it's velocity or the position vector, but essentially this is what you're writing. But remember that the more appropriate way of writing it is you write that P with respect to O, or you can write it as OP or whatever. But there's another thing that is important over here, that you are taking the derivative with respect to not a point but a frame of reference. Okay, it's true that O could be fixed in that frame of reference. This could be O, but what is important is you are doing it with respect to a particular frame of reference. So this notation, it may not be fully given all the time in your textbook, because many a times it's kind of understood, especially if you're dealing with only one frame of reference. They might take that as a default and therefore not put that. But I would like you to do this as a practice even when there is just one frame of reference, because that's a good practice, and eventually almost all the problems that you're going to be solving in let's say system dynamics or even aircraft dynamics, etc., both in courses as well as in the industry, will all be very large degree of freedom systems, and they will involve multiple frames of reference. So having a consistency in this notation in terms of both how you represent the position vectors and how you represent derivatives, time derivatives or derivatives with respect to any scalar for that matter of a vector. Always put the frame of reference with respect to which you're taking the derivative, and always draw these things, even though they might seem trivial or very simple for some of these examples, but because that helps you develop a good habit towards more complex problems and becomes much more simple when you get to them, right? So next, which is what I was saying, that one thing is the frame of reference, the other thing is the Cartesian. So I might have an inertial frame of reference with a Cartesian like this, which is could be let's say I, J and K. Okay, so or in the same inertial frame of reference, I could have an r theta phi or I could have an r theta z kind of coordinate system. So this distinction, one between the frame of reference and the coordinate system, and two between what you're expanding this in which coordinate system and frame of reference and what you're taking derivative with respect to. These could be different in general. So just make sure that how you're expanding this. If you happen to expand this in this, then it becomes very easy to take the derivatives because your unit vectors will not be changing with respect to this particular inertial frame of reference. But if you use a different frame of reference to expand this and take the derivative here, then remember that the unit vectors will also change with respect to time, and you need to account for that. So let's get on to considering the motion in 3D space. Remember that for rectilinear motion, which was what we were mostly focusing on in the previous class, it was just not by rectilinear motion we mean particles moving on a straight line. So therefore we decided that instead of vectors we can just use scalar quantities like speed, the arc length, etc. But when you're dealing with 3D space, you can still use those quantities, but they will become parts of expressing certain vectorial quantities like position vectors, velocity vector, and the acceleration vector. So remember, which is why I put the caution sign over there, that we are working with vectors now. So we're making the transition from what we were working on with scalar quantities in rectilinear motion to a more generic motion when you can have either a planar curve, or which some examples of which you already worked out actually in your homework, and also 3D curves which can be generally there in the space, and you need to deal with that. Now, very interestingly, this is something even before looking at mechanics or dynamics, from a pure geometry point of view, curves have been studied for a very long period of time, and there have been some really excellent works in the 19th century, late 19th century, by Frenet and Serre. These two mathematicians or geometricians dealt with all kinds of generic space curves. So you have a general XYZ system or r theta phi or r theta z system, you have a coordinate curve like that. There are certain coordinates that can be introduced which are kind of intrinsic. So we at the end of the previous class we concluded with the intrinsic system, where we talked about a tangential component and then a normal component. There is something also called as, in a 3D space curve, a binormal component, and so you have a tangential and then there is a normal, which is typically towards the concave side of any curve, and then you have something which is perpendicular to those two. So this we call as tangential t, we call this as normal n, then t cross n becomes your b, which is your binormal t cross n, and this is kind of natural to a 3D space curve as opposed to the 2D planar curves that we were dealing with. So this is a 3D spatial curve. Not that all these three are absent in a planar curve, just that in a planar curve your t and n are within a plane and b is perpendicular to that plane. The entire curve is on the plane, so your b doesn't change. Your b will always be coming out of this whiteboard throughout the path from from some t equal to 0 that we are interested in to some t naught that we are interested in, that domain of t between 0 to t naught. Within that domain, you will see that b is a constant, is not changing with respect to time. Yeah. Very good point. So it might seem that in a planar curve, it's too trivial. But why is a curve not spatial and planar? It's because it is not coming out of the plane, right? So what that exactly means is that there is no some quantity called torsion, or in other words, the torsion is equal to 0. So torsion essentially refers to this plane when you're moving from a planar curve to a spatial curve. So we had started with 2D planar curves. So when we are going from this to this, your b essentially becomes a function of t, or equivalently s, because s is in turn a function of t. So so anywhere you see this distance, you're calling it as s of t, right? So what this actually refers to is, you can see it in a very, very interesting way. See, you had the simplest case you had was rectilinear motion, then you went to a 2D planar motion. So what happened in this is that you are introducing curvatures, right? So now this curvature was within the plane, okay, and which is what some of you also talked about. In fact, calculated the radius of curvature. You called it rho or whatever, right? So for example, here there is a rho of s. Now that is essentially your curvature, radius of curvature, and 1 by rho of s you typically refer to as kappa of s, which is your curvature, right? So now you have that curvature which you have introduced, which was the distinction between a 1D motion and a 2D motion. Now you're taking one more level to the 3D space. So obviously, just like you had introduced curvature to a non-zero curvature to distinguish between the rectilinear and the planar curve motion, going from planar to 3D space curve, you need to introduce another curvature. So that curvature is called as torsion, because what is actually happening is that if you're looking at what is this radius of curvature, essentially what you're doing is at a given point, you're taking two adjacent points infinitesimally far away from each other, right? So now when you have 3 points which are not collinear, you can always draw a circle through them. So that's a property of the geometry, that when you have three points which are not collinear, you would have a circle passing through them, right? So now that circle is typically called as the osculating circle. Okay, and because this is a planar curve, this is essentially this circle is in the so-called osculating plane, right? So as far as the planar curve is concerned, but now you're going from a planar curve to a spatial curve. What's going to happen is that plane is going to be changing. So for example, when you're having something straight over here, it's essentially an infinite circle that you're looking at, right? So now as far as the planar curve is concerned, it is an arbitrary function of rho, but just that all the time your planar, your oscillating circles and your oscillating plane will be the same. In other words, they're not changing. But once you go from a 2D curve to a 3D curve, let's say for example you have a helix. So when you're having a helix instead of a circle, so you're moving out of, let's say you have a horizontal circle, like just like what you were considering, that disk where you had the ball bearing which was moving from the center to outwards. So it's essentially a motion within that horizontal plane. Now that's creating a circle. That's the simplest curve that you can have, because your rho is a constant throughout that path. Now you're trying to go at a certain pitch, you're going out of that. So essentially what you're doing is that you're tracing a helix. and that helix is going to have two aspects to it. One is the curvature, which is still there, that rho of s, and in addition, the radius of curvature, which is the inverse of the curvature, kappa. So just like we introduced the curvature kappa in the plane, now when it is trying to get out of the plane, essentially what we are saying is that the osculating plane is changing. So we introduce a new concept called the torsion, tau. Okay, so just like we had this kappa of s, we will have a tau of s. So we will probably look into that a little later, maybe not in today's class, but sometime soon we will try to look at that. Then you will see what exactly is happening. But the beauty of this work by Frenet and Serre is that they could say that any 3D space curve, even though it's three-dimensional, just by giving this kappa and tau, you are able to define that curve. So in other words, you need only two quantities to define a curve, kappa and tau. And given a kappa and tau, any other curve which has the same kappa and tau, if you can translate it and rotate it, then you can bring it together, you will see there will be one on top of each other. They could be farther away, they could be rotated with respect to each other, but as long as they have the same kappa and the same tau, you can do certain rigid body translations and rotations of one of them to bring it to become identical with the other. So that's essentially the beauty of that. Another important thing that Frenet and Serre came up with are what are known as the Frenet-Serre formulae, and that gives you these three vectors that we are talking about, T, N and B, that is the tangential, normal and the binormal. So you can write them one more thing I just wanted to mention in passing, when one of you was working out, you are referring to S double dot instead as S double prime. Okay. So avoid doing that, because by convention we talk of dots as time derivatives and primes typically as derivative with respect to S. Of course, we can convert from one to the other, but we will stick to that convention throughout this course, including for the homeworks, so that whenever you put a dot, it means a derivative with respect to time, and whenever you put a prime, it essentially means a d by ds. Of course, the difference between them is a product. S dot will come into that, because if I multiply this by S dot, you will get ds by dt into that particular quantity, and therefore there's a difference between the prime and the dot is in terms of a factor of S dot between them. So let's not confuse within that. So here I'm going to talk of a prime. So in other words, a derivative with respect to S, not with respect to time. Okay. If there is a time, then I have to bring in that S dot explicitly as well. So now they came up with a very simple relationship between them, very easy to prove, but I don't know if it's necessary for this course, but we will get to that later. But the result is definitely of significance for an undergraduate program in dynamics. So, and it's not so difficult to prove it either. So this TBN's prime, that is derivative with respect to S, is related to the same three quantities. Sorry, let me put it in the order in which we introduce them. First we introduce the tangential, then we introduce the normal, and then the binormal. So we will stick to the same order over here, T and B. Now this prime quantity is related to this through a constant through a matrix which is a function of S, and this is an antisymmetric matrix, and antisymmetric matrices, as you know, will have the principal diagonal equal to 0. This is even simpler, that it has the other diagonal also equal to 0. Okay, and I told you all 3D space curves are just given in terms of two quantities. One is this kappa of S, which is the curvature, also 1 by the radius of curvature, and you have this tau of S, which is referred to as the torsion of the curve. So then you will see that these things are related to each other, in that this is kappa, this is tau, and this is an antisymmetric matrix, as I said. So this would be minus tau and this would be minus kappa. Okay, so as simple as that. And in fact the first two equations are even simpler than the second equation here. All that it is saying is that the tangential vector is equal to the curvature times the normal vector. Okay, and similarly your binormal vector, it is saying that it is equal to minus tau times the normal vector. So essentially both of these quantities are defined with respect to the normal vector as far as how t and b are changing, and of course from both of those we can derive the intermediate equation as well. As I said, these are not very difficult to derive, but it's not necessarily in the scope of this course. But this particular way of expressing is the so-called inherent or natural coordinate system. It's an extension of what we discussed in the previous class already, where we looked at just the first, this submatrix, 2 by 2 submatrix is what I talked to you about in the end of the last class, where we were dealing only with planar curves and therefore t and n were sufficient. Now that we are moving to 3D motion, it will become important to introduce a b, and in general you could have a non-zero value of tau that comes in. So does that answer your question as far as the oscillating? Yeah. So let's get on with this. Coming to the motion in 3D space, as I said, we are working with vectors now. So we start as always with the position vector, and the position vector in an inertial frame of reference like this. And when we do that, we express in the Cartesian coordinate system of ijk that we have introduced here with caps to denote that they are unit vectors. In other words, their magnitudes are unity. So then you have that, and then of course the velocity is going to be the time derivative of that, and the acceleration is going to be the time derivative of the velocity. Once again, these are incomplete expressions, because I have to say with respect to what I should put an I over here and an I over here to refer to the fact that in taking the derivative with respect to that particular frame of reference, right? So substituting this into this, of course you get r double dot, which also you're familiar with. Now, so as I said, because of the fact that I'm not putting the I, I'm saying that these time derivatives r dot as well as v dot or r double dot are quite vague, because as it stands, because it needs more precision, which means that you have the rate of change that you're talking about, and the rate of change could be both because of the magnitude changing as well as the direction changing, and unless and until you mention with respect to which frame you're taking the derivative, that rate of change, especially of the direction, is not defined, and therefore it becomes quite a vague definition to have. So a differentiation in which frame of reference, so who observes the change, that's very important. The very simple example that you had in your assignment of that disk which was going around and the bearing which was going away from the center, I could be on the ground watching the disk move along with the bearing move. So there are two motions that I have to look at, and it's a fairly complex motion that I'm looking at. But if I were on the disk, like let's say it's like a merry-go-round or something, I'm on the disk and I'm watching that move, that bearing move, it's a very, very straightforward motion that is there, much simpler rather. And when I come out, I need to put those two things together, the motion of the bearing with respect to the disk and the motion of the disk with respect to the earth frame of reference. So that's the important thing. So the overall idea about frame of reference is in terms of who is observing that change, or where is the observer. So what is the observer fixed to, which frame of reference is the observer fixed to, and therefore what is the change that is being observed. So in general, the differentiation in one frame of reference and another frame of reference will be chosen to represent the vector. So in other words, two frames of reference are involved, as I already told you. One is with respect to which you are taking the time derivative. The other is with respect to which you are expanding r in particular coordinate system. So and in general they need not be the same, but if they are the same, taking the derivative is easy, but if they are different, there are certain advantages of that, and we will see examples of both as we go forward. So I think this is clear. Next, let's move on to the next slide. So now the simplest case where you have the simplest kind of frame of reference, inertial, and the simplest coordinate system associated with it, which is Cartesian. The differentiation with respect to an inertial frame of reference, the vectors which are also represented in Cartesian coordinates. So to start with the position vector, it's represented in the ijk system, and the measure numbers are x of t, y of t, and z of t. I've stated this before, but I don't tire to repeat the fact that x, y, and z are called measure numbers, whereas xi, yj, and zk are called components. Okay, and components will always have the same form as the vector, in the sense that this is a vector, that those are also vectors, whereas measure numbers by the very name are numbers and therefore are scalar quantities. So always keep this in mind when you're going to expand two-dimensional matrices as well. So you're talking of the elements of the matrix, those are the measure numbers, whereas the sub matrices, etc., that you're talking about will have a different kind of form. So again, those are also parts of it. But when you're talking of a matrix, let's say as a sum of two matrices or three matrices, then all of them should have the same number of rows and columns, and each of one of them then you can call as a component in some sense. But the elements of a matrix or a sub matrix formed out of a m by n matrix, where with L by k, where L and k are smaller than m and n respectively, that's not going to be something which you can call as components. It's essentially smaller parts of subsets of that, right? Then so in this special case, because you're taking the time derivative with respect to the same frame in which I, j, k are fixed, when I take the derivative to get to the velocity, I, j, and k remain the same. I am not taking I dot, j dot, and k dot because they are all equal to 0. Once again, when I take the second derivative, I take only the time derivatives of the measure numbers and not the unit vectors that they are multiplying. So next, let's look at the analysis in three-dimensional space. And when you're looking at the analysis in three-dimensional space, again, some of the things that we mentioned as far as rectilinear motion continue over here, just that we are dealing with vectors instead of scalars. So once again, differentiation is easy, integration is difficult, but if the acceleration happens to be a function only of time, once again it is easy, just that when acceleration is a function of the position and or velocity, it becomes a little more difficult. But all these are vector functions now, as opposed to the scalar functions that we dealt with in the rectilinear motion. So assuming an inertial frame of reference and a Cartesian coordinate system associated with that, if the acceleration, as I said, is only a function of time, then 3D integration is equivalent to 3 rectilinear motion integrations. Because if you look at the previous slide over here, you see that the I, j, and k were not changing, so I can deal with this problem independently, this problem independently, and this problem independently. For a majority portion, treat them as 3 separate rectilinear motions along the x-axis, along the y-axis, and z-axis, and eventually combine them. It is possible if it's a linear kind of a system, right? So 3D integration is equivalent to rectilinear motion integration problems, and the prerequisite for that is that your acceleration is not a function of the position and the velocity, but only of the time. Now if you bring in that complication, that acceleration vector is a function of the position vector and the velocity vector, then you end up with 3 ordinary differential equations, and more often than not they will be coupled with each other. You can't solve each of them independently as 3 rectilinear motions. One will influence the other, because the same variables, unknown quantities, will appear in all 3 equations, and therefore you have to solve them as a system of equations rather than as 3 independent equations. So if acceleration is a function of the position vector or velocity, you have 3 ordinary differential equations. They are coupled in general, and therefore they have to be solved simultaneously, and this is, as I said, not equivalent to solving 3 independent rectilinear problems. So next let's look at, so that was the simplest case. You had inertial frame of reference and a Cartesian coordinate system. Now we continue with the inertial frame of reference. One level of simplicity is still there, but instead of ijk, we want to go into an r theta z system. So that is essentially what we are talking about. So r theta we introduce essentially in your ij plane, and k remains the same. So as far as cylindrical coordinates are concerned, the only difference is in the xy plane, whereas the z direction, it remains as before, right? So let me okay, so since there is no change in the k direction, I can just deal with the ij plane, and so when I have that, I have your x-axis and the y-axis with an origin O, and I introduce a unit vector which is I hat and j hat, and now if I want to draw a unit circle, obviously it will go through this. So the magnitude of this is 1, magnitude of this is 1 as well, right? Now on the other hand, if I take it to some other location, arbitrary location, some point P of a certain mass m, so what we refer to as particle, so that particle is over there, and now we say that the distance from O, that particle is there, is what we call as r, the new coordinate that we have introduced. Instead of x and y, that is one coordinate we introduce, and the other coordinate, as you know very well, is theta over here. So I can equivalently write p of x comma y as p of r comma theta, right? Now, as I said, we are dealing with 3D motion here, in which case, according to the dextral triad rule, right hand thumb rule, when you're crossing I with j to get k coming out of the board of this plane, that same k is valid both for the r theta system and the ij system or xy system. So I'm not specifically bringing that, so I can always say p of xyz equal to p of r theta z over here, and that's one and the same. Now if I, at this particular location, now if I continue with that, this unit vectors that are there can be translated anywhere that you want. So we are now introducing, instead of the ij unit vector system, we are introducing a er hat and e theta hat system over here. And once again, these are unit vectors, just like I and j. The magnitudes are equal to 1 by definition for all unit vectors. The same thing holds for your er and e theta as well, right? And in your book, McGill and Kang, as well as many other books, the unit vector is represented by a hatted quantity, just to say that its magnitude is equal to 1. Yeah, please go ahead.
And I think I asked this last time. What is the default value? Is for like a unit vector is like 1. So for ER and theta, is that something like that? Or?
Yeah. So your ER and E theta are introduced instead of I and J. So your ER and E theta have magnitude equal to 1. Have I understood your question?
Okay, but so like how E theta is the angle with the x-axis, right? So that magnitude,
Yeah. So what happens is these are going to be, unlike your I and J, which are fixed, your ER and E theta are going to be functions of theta. So at this particular theta, they are there. If I take some other point Q, let us say, then my ER would be this, and my E theta would be perpendicular to that. and this is a new value of theta, let me call it theta star. So your ER at theta star is what I'm interested in at this particular point in time, right? So you see that whereas the IJ would be the same whether you're looking at point P or point Q, I would be just dealing with both of them simultaneously, but when you're dealing with these polar coordinates, you're having at different locations, their directions are changing, but remember that their magnitude is the same. Their magnitude, like all other unit vectors, is equal to 1, which is what we have written over here. But because of the fact that their direction change, the time derivatives of that, or even the derivative with respect to theta for that matter, will be non-zero, and you can easily determine that. Does that answer you, Sid? Yeah.
Can you give an example of like a point represented by the xy coordinates and then a point represented by the organic coordinates using the unit vectors? So like that would be x I hat plus y j hat.
Yeah.
So what would then be in this coordinates?
Yeah, good question. So essentially what you're looking at over here is if you want to put it in the same system, you're having this distance as r and this is angle is theta. So your height would be r sine theta, right? And your abscissa will be r cos theta, right? So in your IJ system, if I were to write this point P from as far as the position vector from O is concerned, I will write R OP as R cos theta I plus R sin theta J, right? And if you recollect, we mentioned this at the end of last class, that if you are putting it in terms of just this ERE theta system, you would see that it's just R ER, right? So your magnitude is R and your direction is ER. Now this is the beauty of it, that you see you needed two terms even for a planar location of a point. Here you need only one term, but it self-contains the dependence on theta. So you have an R here explicitly, but your ER is a function of theta, right? So it is kind of inbuilt into that. So I just have one term to represent the position vector ROP, right? And you can see in terms of magnitude, once again, if you take it, you take the first term, it is square root of, using Pythagoras theorem, r c theta squared plus r s theta whole squared. You take the r squared out as a square root, it becomes just this, and this is equal to unity, right? So just becomes r, which is what I'm talking about here, magnitude times the direction. So essentially this information of c theta I plus s theta j is contained within your ER. So that's essentially what we're saying, because in the first equation over here, I can write that as r into c theta I plus s theta j, right? Which I can compare with the second equation, r and r same. So your ER is equal to, therefore, c theta I plus s theta j, right? So that can also be worked out from here. If you're looking at ER, you see I can draw a unit circle over here. I can draw a unit circle, and on that unit circle, all quantities originating from here will have a length of 1 by the time they meet there. So this particular distance is also 1, right? So now that is nothing but your I, and this is nothing but your J, right? So now you can see that, and this, because this is theta, these are adjacent angles, so this is theta as well. So now if I take that portion, All I'm saying is I need to traverse a distance like this and a distance I have to traverse like that, and then I get over there. So which is another way of saying this vector addition that is taking place, cos theta along the I, sin theta along the j, and then you're moving up, because what we are interested in is not up to the circle but up to this point, right? So up to this point is less than r, less than unity, and therefore that is equal to whatever is the radius of the circle, which is 1 here because they're all unit vectors. So 1 times cosine theta is what you have there. So cosine theta along the I direction, and similarly sin theta along the j direction. So there are equivalent ways of looking at the same thing. One is by writing it in the two systems, comparing them for magnitude and direction, you can get the correlation between them. The other thing is by drawing those unit vectors, and then you take the vector addition, because you know when you go from this point to this point, it's equivalent to going from here to here and then over here to here. So the sum of these two vectors is equal to this vector. Both will give you lead you to the same result, that your ER is equal to this. The same argument can be got in terms of E theta. You see that E theta is in this particular direction, so it's going to have an E theta, which is j times cosine theta minus I times sin theta, right? So your E theta hat can be written as this, right? So once again, it can either be obtained from the directions that you are equating over here, or by vector addition of the unit vectors on the unit circle. From both these cases you are ending up with that, right? Let me see, maybe I think we can continue with this in the next class. Yeah, thank you. Are there any questions so far? Okay, thank you.